Okay. So multiple allele. So what's multiple allele? So what we have discussed previously, we always talk about dominant versus recessive, dominant versus recessive. But in the real case, we don't have one dominant versus one recessive, but we have more than 2 alleles. So multiple allele are 3 or even more allele that can occupy the same gene locus on a pair of homologous chromosome. So the most famous example, actually is humans ABO blood group. So with this ABO blood group, a person blood group may be A, B, AB, or O. Are you clear? So this letter refers to the 2 types of carbohydrates that can be found on the surface membranes, or we call it cell surface antigen. Okay, so if your carbohydrates, you express carbohydrate A, then you get the type A. Carbohydrate B, we're going to type B. Both carbohydrates will be as type AB, and no carbohydrates added here will be type O. And in humans blood groups, we will have 3 allele: IA, IB, and IO. So what actually functions here is, okay, this extra information for you guys, for information only. So we do have an original H antigen. H antigens can be converted, okay, to A antigen, B antigen, or remain as H antigen based on what kind of allele we have. If you want to convert A antigen, you must have an IA allele. You want to convert B antigen, you must have IB allele. If let's say you want them to remain as the H antigens, no change, okay, then it will be cause of the IO. So 3 allele give us the 3 effects here. Okay, so both IA and IB allele will code for the enzyme which catalyze the conversion of H antigens into the A antigen or B antigen respectively. But IO lack of the enzymatic activity, so means that the sugar combination is still remain as the H antigen. It won't change because no enzyme. And we do know that IA and IB, they are dominant over the IO, and IA, IB, we always learn about this, they are co-dominant. So means that, why? Because IA give us A antigen, IB give us B antigen. So means that both antigen express, right? If both antigen express, then blood group will be AB. Okay. So in this case, let's say if the male parents with the blood group A, female parents with the blood group B, okay, and they are heterozygous, okay, because we say heterozygous, so means that if blood group A heterozygous, it must be IAIO. Blood group B heterozygous, it must be IBIO. So in terms of the gamete genotype, half of them IA, half of them IO. In this case, IBIO. So means that the male parent with the blood group A heterozygous, female parents with the blood group B heterozygous. So what are the possible, okay, what are the possible outcome here? Then you can see that 1/4 chance the kids will have the blood group AB, blood group A, group B, and O. Can you see that? Oh, my mistake here again, I. Okay, IBIO. Sorry. Okay, so means that, okay, if, okay, I use this example. A person, the father blood group A, mother blood group B, and he himself get blood group O, don't go and straight away jump to the conclusion, oh, I am adopted ones. Again, not necessary, because we will be able to get 4 different phenotypes. Can I see that in terms of blood group? Okay, with if the father and mother blood group A and B respectively. Okay, so what's the F1 phenotypic ratio? In this case, you can see that AB to A to B to O in the ratio 1 to 1 to 1 to 1. Okay, so with this, I've done for the multiple allele. Again, you can see that you won't get the normal ratio, that 3 to 1 anymore. I get 1 to 1 to 1 to 1. I have even more kinds of the phenotype because I have more allele. Okay, so let me stop recording.